Kelly Collins, and this is my report for Lab 2, Lines of Charge. The purpose of this lab is to build on our understanding of charged object interactions from Lab 1 by using a more advanced model that distributes the charge evenly across the piece of tape instead of it being at a concentrated point. This lab's procedure is to use the initial data and calculations from the previous experiment when we treated the tape's charge as a point charge to find a more accurate value by treating it as a line charge. We found that the tapes, when in equilibrium, have a charge of about 4 times 10 to the negative 8 coulombs. Now we'll move on to the fundamental principles and assumptions we use in this lab. We use Newton's second law to simplify the equation to find the electric force since the tape's acceleration is 0, making the net force 0. We then use Coulomb's law to find the charge from the electric force. The assumptions made for the line charge are that we ignore air resistance and that each tape has the same amount of charge evenly distributed along. We take a look at the experiment next. The experiment where we collected our data is the one we did in Lab 1. The first step for the experiment is to charge the tape by pulling it off a base tape. We then determined that they were positively charged when the tapes were attracted to the negative pin. Next, we move one piece closer to another until the top piece floats and reaches equilibrium. The key observation from Lab 1 was that because the tape was in equilibrium, the acceleration is 0, making the net force 0 by Newton's second law. We then realized that the force of gravity is equal to the force of electricity. Then, by manipulating the second equation on the left, we find that the charge on the tape is 1.8336 times 10 to the negative 8 coulombs when using Coulomb's law. Let's now compare the glow script models for a point charge and a line of charge when using the previously stated result. As we can see, the charge we found using Coulomb's law works fine for the point charge model from Lab 1, but not the line charge model from Lab 2. The charge is not large enough to counter the gravitational force in the line charge model. So we need to estimate another charge for this model to cancel out the force of gravity. We'll use the Lab 2 code to do this. Through trial and error, we find that the net charge on the tape should be 3.999877 times 10 to the negative 8 coulombs. We use the E-field function to find the electric field of a charge and use the line charge function to create a line of charge. The next part of code creates the line charge for the top piece of tape and the bottom tape. Each tape is modeled as multiple point charges placed along a line, with the top acting as the system and the bottom as part of the surroundings. We then calculate the net electric force on the top tape due to the bottom tape by adding the forces from each point charge from the bottom tape's line of charges. We also create the arrows representing the individual electric force, the net electric force, and the gravitational force. As we can see, there is an electric force arrow coming off each point charge in the line, with the new charge 3.999877 e to the negative 8 coulombs. The magnitude of the net electric force is equal to the gravitational forces, a magnitude at 5.72 times 10 to the negative 3rd newtons each. At the end of this lab, we have determined that the tape's charge, when treated as a line charge, is 1.18 times the tape's charge when treated as a point charge. These charges differ so much because different assumptions were made for each. The line charge model represents the reality of the situation more, making it closer to the real value. Thank you for listening.